Hello. So today mm, presenting Anvil, a paper which talks about verifying liveness in the context of cluster management controllers. In essence, this paper presents the framework to verify liveness. It is built on top of virus verification tool integrated with Rust language. And it includes TLA embedding for temporal logic of actions. It provides models for the environment of those controllers and a library of lemmas which help to prove correctness of your controllers. As a case study, they also implemented three controllers and verified them for correctness and liveness, for safety and liveness. As a bad scenario, they present a controller which has to configure some services and create configuration map here. If you see in this pseudo code, basically it checks if service exists. If not, it creates the service, creates the configuration, and does then the following steps. In principle, if a node crashes in unlucky place, like between those two commands, next time the service will be already created, so this check will be false, and the config map will be left not created here. So successful execution is shown here, like configure some services, then another service, then update the configuration. And if the crash happens at the wrong time, we skip creating configuration at all. And this makes the controllers crash or fail to converge with their tasks. Basically, the controllers in this context are kind of Kubernetes controllers which are responsible for changing cluster membership. Like if the user asks to rotate this cluster of Zookeeper or something to another servers or increase that set of servers, the controller is responsible for adding new nodes, removing old nodes from the configuration, and end up eventually with the configuration the user asks. Usually for the verification, safety properties like invariance are verified because they are a bit easier to verify, but this paper considers the liveness properties here and not just model check, but also to prove them. How do they propose to model the liveness of those algorithms? That in principle, in the cluster, the user can keep changing the desired configuration. And in this case, the controller might fail to catch up with those new wishes of the user. So for the system to work, the desired configuration should be constant for some time. And then it has a chance to converge to needed configuration. So in this paper, they propose that if the configuration currently asked by the user remains for all the remaining time the same, it will not change in the future, then eventually always the system will converge and will stay in that configuration. It actually resembles some eventually consistent systems and similar. That operator leads to is modeled in temporal logic as always if A happens, then eventually Q happens as well. Okay, so the model itself, or the logic on which the proofs are based, is based on TLA, the temporal logic of actions. Actually, not on the TLA language. Language is TLA plus, but only the logic is used here for describing that temporal part of the system. So in this formalism, you have to have a state machine, and to make the controllers which do the transformation of the cluster till the needed configuration, to make that implementation a bit more constrained and easier to verify, the authors introduce the interface for the controller, which should be implemented by particular controller, and it has typical state machine interface, like initial state is returned from this callback. Then we have a function step, which takes desired configuration, the current state, the response from previous request, and returns some another state and request to be made in the next step. Also, to make those steps atomic, this interface ensures that in each invocation of that step, only a single call to external services can be made, because you cannot call something directly. You can just return a request which will be executed by the environment. And the remaining two functions are just to check if we are done with this state, and maybe we are in the failure state now. This picture describes all the content very well. So the goal is to have the controller which is executable and performs its tasks. It is implemented in Rust, and for it to be verifiable, we have to implement the controller itself here, and yeah, implementation should use that interface I presented before. Apart from that implementation, we have to provide also the model, which is implemented in Ghost code, so it is not compiled to the binary, but used in compile time for verification. For that, this controller kind of abstracts the implementation of the controller. And we also have to provide conformance proof that the model actually is abstraction of the implementation. So now, when we have a model already implemented, we have to prove its liveness, first of all, and also we can prove the safety properties here. So we define them and prove also manually. To define the safety and liveness properties, we have the TLA embedding provided, some formalism of temporal logic of actions like execution, temporal predicates, and operators. And we also have quite a big set of lemmas which can be used to make the proof effort easier. And also the controller usually works in some environment. It accesses other built-in controllers, etc. It uses the network. So the model for that is also provided here. Yeah, so let's move forward. The controller itself, like the model of the controller, is implemented in Ghost code, which is shown here as an interface here. And as you see, it resembles that initial interface closely, but it is not compiled to the resulting binary and is used for proofs only. Uh, for the TLA embedding, execution is defined as an infinite sequence of states indexed by numbers. Then predicates are defined which are temporal. So you can have some predicate of execution and also some temporal operators introduced like leads to, which converts some temporal predicates to other predicates. Below, that's a fragment which describes the same ESR property, like if always desired state is the same, then eventually the cluster will match that configuration. So yeah, it is defined in the context of a model for all configurations. If always desired state is the same, then it leads to always matching specific configuration. For the network, they provide models, interfaces, and related lemmas for the network, considering the message delivery, which should be with weak fairness. Cluster store, like centralized storage used to maintain the cluster information. Other controllers include garbage collectors and others used in at least in those controllers they were verifying. And also client requests a model there as well. So the user of this framework has this provided and can focus on own controllers only. For the faults, they consider controller crashes and request failures. So those controllers can crash at any time, and we will try to recover those controller executions and still converge to proper state. Talking about the assumptions, the framework introduces weak fairness for the controller we model. So it means if some action in our controller is enabled or can be executed for infinite amount of time, then it eventually will be executed. Yeah, another assumption made to make proofs possible is that faults are eventually disabled. The same like with the desired configuration, if we change it infinitely often, then nothing can converge to that configuration. The same way, if the controllers crash infinitely often, then you cannot prove that it will converge somewhere. So some number of faults might happen, but then at some point, they stop happening. Yeah, and similar assumptions for stateful set controller and others introduced. So we expect that if our controller is not doing anything, eventually the environment will become stable, and then we can converge in that stable or steady environment. Quite a lot of reusable lemmas is provided in this framework as well. So some of them are related to temporal logic, and that's only an example is shown, like transitivity of leads to operator, but 70 plus of those lemmas are on temporal logic, and quite a lot of lemmas also provided which are related to the environment model. For the garbage, this example includes the garbage dilemma related to garbage collector. So all the objects will contain an owner if each request basically sets existing owner for an object. So with this lemma, for example, the user of this framework, when specifying its controller's specification, it will have to prove that it sets proper owner on each request, but remaining liveness can be proved using this lemma. Then they introduce a kind of generic approach how to prove that eventually stable reconciliation for the controllers. Basically, two steps are used here. So first of all, we have to prove that environment is eventually stable. So like mentioned, garbage collector stopped updating something, and faults have stopped occurring, etc. And then, assuming the stable environment, we have to prove the liveness of our controller. Yeah. To show that this approach works well, they implemented three controllers for Kubernetes. The code itself is aligned with not built-in, but widely used implementations of those. So for Zookeeper, RabbitMQ cluster, and FluentBit. And this slide shows the basically number of lines used to implement those controllers, also to prove them, and what is the amount of lines of code which is just trusted and not proved to be correct. So all those models for the environment, for example, it is assumed that their models reflect the actual implementations of those controllers and services, but that's not proven, just tested and presented. Yeah, so from this slide, it looks like not too much of the proof code is needed for such verification. After implementing and proving correctness and liveness of those controllers, they implemented unit tests and ran them and found a bug. That's interesting part, and it's nice that it is mentioned in the paper actually. So while Zookeeper controller was proved to be correct, it still had a bug, and basically that bug was because of imprecise implementation of that service step. So the trusted code had some flaw, and because of that, proof passed, but actual execution failed. And for the performance, they show that it is not too bad. That unverified reference implementations were a bit faster, but they had some optimizations, and those optimizations complicate proofs. So the verified implementation is with less of those optimizations, but still works quite okay. That's it from my side.